Thank you all for joining. We're excited today to talk about accelerating drug discovery and reaching drug outcomes faster using WEKA on AWS. My name is Pruitt Chamness. I'm the Director of Cloud Sales.
My name is Barish Kuler. I'm the HPC Practice Manager at CloverTex.
So let's dive right in. Baris, before we get into the workflow, would you mind just talking a little bit about CloverTex, who you guys are, what you do?
Sure. We are at CloverTex. We build the scalable, reliable, performant research clouds for the pharmaceutical industry so that they can accelerate their drug discovery and focus on science instead of building infrastructures.
Great. Let's jump right into it. So we're here today to talk about drug discovery, and at the center of this is cryo-EM and cryomicroscopy. For those in the room who don't know what cryo-EM is, Baris, can you talk a little bit about what it is and how it fits into the context of drug discovery?
I'll do my best. There are some experts over here. If you have questions in depth, definitely Moria-san can answer those questions a little bit more in depth. But basically, cryo-EM is recently been popularized and able to flush frozen liquid of protein molecules and going through electron microscopy to capture images of particles, thousands of particles, and determine that to 3D structure of a protein. Once you know the 3D structure of a protein, then you can target for the drug discovery different compounds for offsetting that.
So we've got proteins that form together to make diseases, and we're using a cryo microscope to map them, and then we're taking known small molecules and finding crevices in proteins where they can block the proteins from forming and ultimately stop and cure diseases. Now we're going to talk a little bit about the project at hand and how WEKA is being used to accelerate time to insights and patient outcomes relative to drug discovery. Baris, can you talk a little about the architecture that you used to do this?
Yep, over here you can see it's a little bit eye chart complicated. I can explain a little bit more in depth if you want to dive into it. But in short, we have on the right side upper corner code pipeline that's determining how the overall infrastructure as a code is defined, and then it builds the whole thing that you see all the AWS services. And on the left side you see that on-prem you have the microscope in the lab that's generating the data, and then we build the pipelines using various mechanisms. WEKA is one of them, to bring it to the cloud and make it available to the parallel cluster behind the scene. And cryo-EM and Reliant, these applications can run on top of it without needing to know any of the underlying structure, essentially.
And so I think it's important to call out the fact that doing these types of workflows in the cloud is a relatively new idea. Baris, can you talk a little bit about how these workflows have traditionally been done, and then we'll get into some of the challenges associated with that?
So in the past, or even some today, right? Most of these are run on-prem, used to, and traditional NFS or NAS devices are being used, and GPUs. And of course, as this area is expanding, it's not easy to just purchase more GPUs, right? But the cloud is giving the flexibility to the companies to expand quickly, and then they can shrink it when they don't need to use it. As well, we have multiple options in terms of the file systems like WEKA. That can expand the throughput that the customer may be looking for, but on-prem you might run into other workloads affecting the runtime of your application, essentially. So
this historically has been a fairly on-prem centric workload. So we're really pioneering in this space, bringing these types of workloads to the cloud, and customers are taking advantage of the same elasticity and speed of instantiation and deployment that they do for more traditional workloads. Let's jump into the pipeline for a second, and Baris is certainly an expert here, but ultimately what's required as part of this pipeline is different parallels on which performance is being measured as it moves through the pipeline. This is a more traditional architecture, and you see data copy and movement through the process. Baris, can you talk a little bit about this and the challenges that customers face relative to this?
Sure, yeah. So during the data processing of the cryo-EM, from the image collection to the model generation, eventually, you go through multiple stages, steps of the workflow, which is importing the raw image files, generating the micrographs, and then doing the 2D classification, 3D classification, and then 3D modeling. Each one of those have different characteristics in terms of I/O profile. So initially, you have a sequential long reads type of I/O profile. Towards the end, you'll see that the more random I/O, smaller I/O is being more dominant. As a result, you need a file system that need to span across and able to handle different types of I/O that you can throw at it.
And so to ultimately speeding up this process means quicker time to outcomes, more drugs created faster, and a quicker time to market for drug companies. And what's happened historically is file systems are built to do one thing really well. And so oftentimes what will happen is these drug companies or the technology providers that are supporting drug research will tune a file system for one portion of the data pipeline. Maybe it's high I/O or random or sequential reads and writes, and they will have to suffer with the notion that the file system was tuned for that one specific phase, and then it'll move slowly during the other phases. The other thing that we see is a tremendous amount of data copy and data movement, and ultimately data operations can become very complex associated with these workflows. Now we get to the fun part. How are we using WEKA to ultimately accelerate and simplify these workloads and allow researchers to do what they do faster and more simply? The unique thing about WEKA is we're able to optimize performance with zero tuning and zero copy for every phase of the architecture. Baris, can you talk a little bit about what you saw as you started to test WEKA?
Yeah, so it was actually quite straightforward. We get the CloudFormation template, determine the size, how big the file system we want, and within 20 minutes we had the file system up and running and ready to essentially run the workflow on top of it. So it was fairly straightforward, and the nice thing is you get good results right off the bat instead of tinkering to essentially make it work a little bit faster.
Great. So now I'm just going to do a quick overview on WEKA. What is WEKA? We're a high-performance data platform that can run on AWS infrastructure. And we're running across EC2 instances with onboard SSD storage and delivering the maximum amount of performance capable. And we're able to independently scale performance and then tier to S3 on the back end to optimize cost. And so ultimately what this does is it allows us to deliver the maximum amount of performance regardless of how performance is being measured throughout the pipeline. And you can do it with zero tuning. So this means quicker time to insights and outcomes, less data operations and data management, and a simplified architecture. And then by tiering to S3, we're able to make it more cost effective than existing solutions. So Baris, I'd like to now get into the specific benchmarks that you did. Can you talk a little bit about the project that you undertook?
Sure. What we did is we take the CryoSpark application from structural biotechnology. Thanks to them, with generous licensing that they provided us, we were able to essentially get the benchmarking done at the scale that we wanted to achieve. And for this case, we used the Empire 10,288 data set that has 2,700 movie files and about 470 gigabytes per the workflow data set size. And our goal was, you can find single benchmarks out there in the cloud, but there wasn't any large scale, tens of users running jobs at the same time. So we wanted to, if we go to next slide, please. We wanted to make it in a way that it's representative of a 5 to 10 users running jobs at the same time, and make sure that the file system we put together is able to cope with this and not hinder the performance of the any team members, right? So as you can see, each vertical line indicates one workflow end-to-end from the TIFF ingestion all the way to model generation. And we had 10 of these, and on top of that, we have also a live session that was ingesting the data. And all of these were either read from WEKA or written to WEKA, essentially all the results.
Thank you. And something that's unique here, and I want to give CloverTech some credit. The notion of testing multiple users, up to 10 users, is really important. We've got benchmarks for single users, but we wanted to replicate a real world scenario. And Baris talked about the CryoSpark software. and he mentioned how generous we were to be able to get access to it. This software is quite expensive. And so it's really important to be able to make multiple users effective and to optimize the licensing associated with this software. And so by accelerating the data pipeline and the ultimate drug discovery process, we're able to make better use of this expensive software. I think another thing that's really important is to look at some of the results in the actual runtime. Barris, can you put this chart into context for us?
Sure. In the previous chart, we had 10 users, and what we did is actually 5 different instance types we use in the Slurm. As a result, we had enough data set on each instance types running the same workflow at the same time, so we see that how the instance type actually affect the results, the run from end to end, how long that workflow takes, right? So as you can see, G5 4x large is about 7 hours all the way. That has single GPU. All the way to the right, you'll see that 4 GPU as well as 8 GPU instances we benchmark. And going from G5 24x large, that's the third column, to the fourth column, you see that even though we doubled the number of GPUs, the workflow, because of the application limitations, it didn't scale more. Different stages of the workflow has different GPU requirements. As a result, you cannot make everything, utilize the 8 GPUs as efficiently as possible. So with WEKA,
ultimately, we were able to max out the performance of the CryoSpark software. And for anyone who doesn't know, GPUs are, 1, quite expensive, and 2, they're scarce. They're hard to find. So being able to maximize the value and saturate GPUs is extremely important, not only in a model like this, but in any AI model, any machine learning model that's using GPUs. Barris, can we talk a little bit about some of the price per performance things that you learned?
Yeah, so what we did is essentially we take the on-demand pricing of the instances and calculated how much that the workflow end-to-end would have cost if you run on different instances. And clearly you can see that G5 4x is the lowest cost, and that's one of the recommendations we make to our customers. As well as if you want to get to your job a little bit faster, G5 24x large, for example, is another option, even though you're paying twice as much for it, but you might have, because of project restrictions or requirements, deadlines, you might still want to invest on that and get your job run twice as fast, for example.
So let's talk about the results that you saw.
Yep, so as I just mentioned, right, G5 4x large delivers the lowest cost and of course longer runtime, but if you have enough users in your team, some of them will be running with that mode of operation, right? So to get the best value for your for what you're running. And then 24x large, G5 24x large is a good balance return on investment, delivers the reduced runtime, but a little bit more cost. 40x large with the 8 GPUs, we didn't find it very, very useful because runtime didn't improve much, but then cost also doubled again, right? So basically we lowered the cost of the HPC file system solution, lower runtime workflow steps, and also further reduce. These results can be further reduced by purchasing reserve instances on top of it, right?
So I think it's fair to say better, faster, and cheaper is good just about any way you can slice it.
That's right.
Finally, let's put these results back into kind of business value and business value summary. So what does this mean for the future of drug discovery, right? This is a model that we're going to see across all large pharmas and research institutions. And ultimately what we learned through this project was that we can stream data transfer faster, we can provision capacity and throughput independently, which allows us to scale up and scale down to meet workflow needs and ultimately optimize on cost. We can make the latest data available to researchers quicker, allowing them to ultimately drive results faster. We can automatically evict data, which allows for better caching, faster run times due to reduced I/O and latency. Again, faster time to outcomes for customers and drug researchers. And then ultimately, we're able to deploy Cryo-EM and make the most value and the most use out of that licensing, which is extremely important. And then finally, on the back end, from a management standpoint, we can implement patches and at the click of a button. And so the actual operational aspect of it is much simpler. And what does this allow for the actual drug discovery companies themselves? It means getting to drug insights faster, getting time to market faster, bringing patient outcomes to reality faster, and allowing scientists to focus on science and not the underlying infrastructure associated with projects like this. Thank you, Barris, so much.
Thank you.
Really appreciate your support, and thank you everyone for listening today.